I will start PAT model checking system, which is multi-domain model checking system. Firstly, just a bit of background. The PAT language is based on Tony Hall's communicating sequential process. Some of you know Tony who invented the Hall logic, which he won the Turing Award for for inventing the Hall logic, which is a foundation for program verification. Hall also invented a sequential communicating sequential process, which is event-based calculus. It provides a foundation for concurrency and communication, and many parallel programming languages is based on this CSP, communicating sequential process. For that, I think he won the Kyoto Prize, mainly for the CSP contribution. Hall's most recent work is on unified theory of programming, which again, our Python language CSP shop also had a formal semantics based on unified theory of programming of Tony Hall. But our verification technology is based on Edmund Clerk's work. Particularly, one of the engine under PAT is using binary decision diagram, which is an efficient data structure to scale up model checking. For that reason, Edmund Clerk won the 2007 Turing Award. For those people not in computing, Turing Award is Nobel Prize in computing. Ed also won the Franklin Institute Bowers Award, which is another big award for technology. The reason behind is because the model checking not just academic contribution, but heavily used by industry, like i7 in Intel core execution cluster is completely model checked by the Intel in-house model checker. Microsoft also have a driver correctness, which based on model checking technology. Even Bill Gates talk about how important the model checking systems in Microsoft since Windows systems. And we've been pretty lucky. I think some of you, I don't know, in this group chat, is part of my early team in the PAT. We have a Tony Hall and Edmund Clerk visit my group multiple times in the past few years, has given many advice, and we are very appreciate for their collaboration and many very useful suggestions. The PAT model checking system, as many of you, developed by together with two of my former PhD students, Liu Yang and Sun Jun. The idea is that we want to develop a generic model checking systems, unlike Intel and Microsoft, because the Intel model checking system can only be used by Intel company, which is a domain-specific system checking i7 core execution cluster, where Microsoft model checker can only check the driver correctness, a very domain-specific model checker. We want to develop a generic model checking system which catering for many different application domains, including concurrent systems, real-time systems, probabilistic systems, security protocols, sensor networks. We have 15 different verification engines, has 1 million lines of source code. And actually each verification engine is supported by one of the PhD thesis. We have been lucky have a commercial version has been bought by major Japanese companies like Sony, Mitsubishi, NTT, Toyota, bought year after year the commercial version. The education also has been downloaded by many users. We also receive many very good feedback. Jun and Yang luckily is in Singapore, not unlike my other students probably go to overseas, Australia and New Zealand. Since Jun and Yang still in Singapore, we have a very close collaboration with still many ongoing joint projects right now. So PAT has been developed also further below by Zhe and Hedron have this NPAT, which later I'm going to talk about a project with the particular autonomous systems. Let me start, since it's a little tutorial, let me start with a simple application using concurrent module. The idea is to fully model and certify some properties about a recent technology which introduced into the uh, automobile. They call keyless systems. The picture here actually exactly the car we bought it, my family bought it in 2007. At that time, is kind of new to us because there is no key to insert to turn the engine on. Instead, there's a button. You can push that button. As long as you have a sensor inside your pocket, the engine can turn it on. You can lock the car when you go outside by pushing a little button outside this door, this little button just outside the door. As long as the key is inside your pocket or in your bag, you can switch, you can lock the whole car. One nice features of this particular new system compared to the old ones is that the key never lock inside. So that's what they're supposed to guarantee. However, there also a new behavior which introduced. I think a real case is that I remember clearly one day my wife and I go to um, I think a Saturday I want to go to my office. My wife want to go to a shopping mall, and so I said, yeah, I need to go do some work. So I go to my office. I can go for shopping, and my wife showed me off. I drive the car to my in front of my office. I get off the car, but I didn't switch off the engine. So my wife so continued to drive the car to the shopping mall. And later the telephone rang, and my wife asked, "Hey, where's the key?" Yes, I think the key inside your pocket. And at that time, I think I would try to ask my wife maybe just leave the car open and maybe unlocked, just go for shopping. But my wife insists that it's a new car, I don't want to get it lost. So I take a taxi and go to the shopping mall and actually drive the car to my office, later pick up my wife after she did the shopping. So what I want to do is use model checker to automatically to verify two properties. The first property I want to verify whatever you concurrent processes interaction with the multiple person interacting with the car. What I want to verify is that the key never lock inside. I want to certify that property. The second one, I want to display a new emerging behavior which never happened before. That is, you can actually driving the car without a key. Like my wife drive a car, the key is inside my pocket, which never happened before, right? The old system, you have to insert your key into your car, and that will never happens. To do that, there's a model. We can model that there are two driver, husband and wife. Initially, the driver is far away or near the car or inside the car. The engine can be off and on. The door can be closed but unlocked, or closed with the locking state, or the door can be open. And the key sensor, the key fob, can be inside the car or could be very far away on the piano. We may have two drivers in the beginning, husband and wife, like zero represent husband, one represent wife. Engine equal off initially, door initial state equal lock, and the key equal zero. And moving equals zero initially, and there's full tank. Okay, so that's the initial state. One concurrent process, one particular concern is that we can model the driver position relative to the car. I mean, the overall architecture is that the whole model, the car is about the parallel processes. Doesn't matter how many drivers, that's a zero represent husband, one represent wife, or could be later when my daughter get a license, so she could also drive to be 3%. And the driver position is a process which model the driver's location relative to the car. And the motor is another parallel process, which motor the engine could be on and off and fill up the petrol and start to move. The door has a process which is another parallel process running in parallel in the case to changing the state when the door can be closed and open. You can open from inside, open from outside. Initially, the driver position is the driver is far away and can perform event. So here is a condition, owner equal to phi is a predicate. Capture the condition before the event called towards. I is just index of a process parameter. So I if equals 0, maybe represent the husband. I equal 1 represent wife. So let's say equal 0, like a driver husband initially is far away, can walking towards the car, and the state of this driver's location position will change from far away from the car to near the car. So that's one of the event. Another process scenario is that when driver is near the car, it can go away. And the driver's position relatively changing from near. And here's assignment, which is a piece of program like Java or whatever Python program uh, to change the position from near to far. There are other processes which once you near the car, when the door is open, when the car is not moving, then you can get into the car. Then the driver position will change from near the car, become inside the car. I put moving equals 0 just to be really conservative, right? So if you guys watching 007 James Bond movie, they can get into the car while the car still driving even with fast speed. So you could get rid of this particular predicate to allow the behavior like 007 style of scenario. Similarly, to get out of the car is when driver is in, the door is open. When car is not moving, again, I'm pretty conservative here. And you can get out of the car in driver position. When you get out of the car, is near the car. Again, moving equals 0 is conservative. Yeah, if you want to James Bond style, then can get rid of this particular predicate moving equals 0. Key for position is that start key initially with maybe I if I equals 0, I equal husband. Driver is inside the car, and if inside the car, you can put the key inside the car. Another scenario is that when the key is when driver with say I equal husband, when husband has a key and the driver husband is far away, he can put the key away from the car to maybe put on top of the piano. That's where we used to. And when key is far away, or the driver is far, or key is inside the car, or driver also inside the car, then you can get a key. Then go to the key position. As you notice, model checking not just model the embedded system of the keyless system, but also can model the environment, the key fob the positions, the driver's position, particularly purposely, the driver position is not part of the embedded system inside the automobile, but it's really the environment interacting with the embedded systems, the keyless system. So good about model checking is that you can actually model the environment as a parallel process to interact parallel with embedded systems. Door operation perhaps a bit more complicated when the key is, this with husband, driver is near the car, husband near the car, the door is locked. When the car is not moving, you can actually unlock and open the door. When you open the door, here's a piece of program assignment, assign the door equal open. If near the car was unlocked, when the car is not moving, you can just open the door. And you can also, when door is open, when driver is inside the car, you can also inside open the door when door state will become open. You may question that maybe we should to have a key equal I inside this particular predicate here, right? To make sure you have the key, then you can open from inside. Well, there is a kind of a trade-off. Let's say my daughter is inside a car, um, I go to a petrol station, get ice cream. Australia is pretty hot. I know now it's winter time. Singapore is pretty hot. And I could maybe I take a queue out to buy ice cream. If it's if the car is getting too hot, even my daughter don't have the key with me, right? She should be able open to open the door from inside. Therefore, we don't need a key equal I inside this predicate. Similarly, um, for inside lock, right? We don't really need key equal I to be able to lock the door inside. If I leave the door open, my daughter inside, but there is a vicious looking guy outside, looks to be dangerous, my daughter just can lock the car from inside. So that's the point. So you do need key equal I for that kind of condition. So this is pretty much the behavior of capture the door operation. The motor you can turn it on when the engine is off, when you still have the fuel, and you can start to drive when engine is on. You can have a short drive. I just divide into short drive, long drive, just make a little bit interesting to in the Singapore scenario. Singapore people during the family time, during the weekend, they usually drive to shopping mall. Most Singapore family go to shopping mall. It's air conditioned, have some food in the food court or restaurant. Some Singapore family may could take a long drive to KL or to Malaysia. So that probably take a half of the tank. So I put a condition fuel mass greater than 5, more than 50% of the tank. We can even capture the government regulation. In Singapore, you should be actually 7.5. That's three out of 4 quarters of the tank need to be full if you drive out of the Singapore. So that's the rule. But usually the policeman, if you more than half the tank, they usually let you go. So that's the condition you can put there. So you can drive to Malaysia. Here's a piece of program, and maybe take half the tank, go drive to Malaysia. You can also stop the engine, refuel the tank, and so on, right? So that's the behavior of the motor. Now you put everything in parallel, then you can check whether the key lock inside. Another thing I'm interested is, the new behavior where I'm in my office, my wife drive the car to the shopping mall without key. Is that allowed? What I wanted to do is want a motor checker to automatically verify those properties. If it's allowed, give me display a particular trace. So let me do a real time demo. So here's the motor checking systems. Here's the keyless systems. All these examples I'm using is our 200 building example in the past systems. Is our so this is the one the system building 200 building examples you can play around the study pad. So it's very easy to study pad. Compared to many model checkers, they have a very nice interface. Show you the model which I just presented in my slide. And one thing is key lock inside, right? Here, let's so what's the key lock inside? It's a predicate. It's a predicate that the key is inside the car and door is locked. The husband, owner zero represent husband, is not in the car. And owner one, wife, also not in the car. If that's the situation, right? Husband both not in the car, but key is inside the car, the door is locked. That means what? That means the key is locked inside. We want to check this property, the key lock inside is never reachable. So it's invalid. That's what we want to verify. So we want to verify key lock inside. We want to say not valid. There's no legal trace reaching to that particular state. And here actually display a particular car actually reaching to that particular state. Um, yes, checking through. You can give a shortest trace to see why that happened. Okay, so what this did is that it actually they said that even though the model completely looks like no problem, key will not lock inside, but the model has something extra than what I just present to you. It has this through the key action. That is, you can partially open the window of the car, then you can throw a key from outside. Imagine everything locked, right? Then you go outside, but the window is open, partially open, and you put the key inside. So that's the idea. If that's allowed, actually the key can lock inside partially because the window is partially open. You can drop the key. So that's the trace which may leading to that. Um, However, if you remove this kind of a special corner case, without this, without this through the key from outside, through the key, through the window inside, then you should be able to guarantees. So this is the one. This is the original model I demonstrated. So this is the extra stuff. It's my tutorial question actually in my CS421 class, a challenging question. So with the original model, without opening the window partially through the key deliberately inside the car, those very corner cases, without these kind of cases, it should guarantee the key never lock inside. Let's verify again. Key lock inside. This time, guaranteed not valid. The key never can lock inside without that special open the window partially through the key from outside. So that's one property. Another interesting property I demonstrated earlier is that, the scenario, I go to my office, I drive to my office, we didn't stop the car, my wife continued to drive to shopping mall. See that? And that is a last property, right? Driver without key. So car is moving, driver, my wife, owner one represent wife is inside the car, owner zero is far away, key equal what? Zero. So key with husband. So that's the situation. We want to see whether that is reachable. Let's verify. So that's my wife driving without key, but key actually inside my pocket. I'm sitting in my office. Again, they give me a random kind of, oh, this time it is reachable. There's a true story there, but I want to show the story. Maybe that's what happened to me and my wife. Let's verify again. Okay, here's the trace. Let's display this. So Pat, just show you the initial simulation. You can say, tell me what happened. Um, we have a trace. Okay, the first event is that wife walking towards the car, right? The second event is husband walking towards the car. Okay, I follow my wife walking to the car. Then the husband, the third event, husband open the door. Then wife get in. That's pretty Western style. And then husband get in, right? That's the next event. The husband tell the engine. That's pretty much exactly what happened to me and my wife. Then what happened is that the next one's a little bit different. The husband get out. Then wife start driving. Well, the interpretation of this story is that I guess is that my when I turned the engine, I suddenly remember I didn't bring my office key, and my wife actually a little bit frustrated that day. You know what? It's not that far away. You need to do some exercise. You work to your office. So she start driving. So that's the story. Not exactly what happened to that weekend, but something very interesting. Model checker can automatically display a story to show you this emerging behavior that never happened before in the old system. So that's something very interesting. Okay, so that's the first example impact. The second example, I want to demonstrate the model checker are very good at finding bugs, right? Finding whether the key lock inside or not lock inside, a particular scenario where the driver can drive the car without a key and checking this kind of status. It really, the reason model checking win the Turing Award, the Nobel Prize in computing, is because it's automatic tool to finding bugs. What we want to push, actually, we think model checker are also very good solver, a decision maker, and making precise decisions. I'm going to use a following example to demonstrate. To use model checker this time to find something good happen, be able to solve something is not easily to be solved. Okay, here's a little puzzle for everyone. This is inspired by the culture of New Zealand, Australia. They have many ships. There's a loyal dog shunting. The idea is that you blow the whistle, the dog will put all the ship into a particular safe area or push all the ship back home. Let's imagine the home is all the cross positions right in the middle. Here's all the ships randomly, eating grass. So the idea of the dog is running around pushing white sheep back to the central position. But he can only push certain rules, right? Just make it interesting. The black dog can only push one of the sheep at a time. He cannot jump over the sheep. He cannot go diagonal, can only go one step at a time to the neighbor. To capture that, we need, here's the legal position means that here may be mountain, here may be cliffs. So he can only move around the legal position inside the board. Impact, we can, just like a C# or Java program, we can use a two-dimensional array to capture the board of the game, right? Initially, black in the 3-0 position, and white sheep in those positions. Model checking is that from initial state, the black position is here, white position occupy those positions. The only possibility for black to move is either push the white to this position, or simply black position just a dog move up without pushing anything. In fact, the tricky of this game is that if you push the white shape right to the right-hand side, the game become unsolvable. You'll never be able to solve. So it can only be able to go up to have a chance to solve the puzzle. The reachability analysis basically, so give me the initial configuration of the white shape positions. The black dog can push those white into the middle position. If can achieve the final state, then we want to find out the traces of the different events of the black dog. So we can easily develop a model, a two-dimensional array, O representing outside position, A representing available, where W representing the Y position, that's Y position, where the black position represented by R, row number equals 3, vertical number equals 0. So this is the model that you can capture the move up. Basically, you check the upper position is available, and then you can just go up. Okay, push up, you're basically pushing the two position above whether it's available, and the position right above you is Y shape. You can push up. You can push the Y shape up. So certain condition give the event and piece of program changing the position. As you can see, the model of this is just a purely specification without backtracking algorithms, just state what the rules of the game is. And the question is, can we solve the game using model checker automatically? So this is almost like in large language model, we just specify what the rules of the game. We want a large language model to be able to solve this puzzle for us, right? So that's the kind of idea. We just give the specification. Then we want a large language model to generate a program to solve it. But here, just a specification. So model checker is almost like that, magic. You give the specification, then you ask a question whether this puzzle is solvable, and the model checker will be able to do that. And you can check many different kind of property. Want to reach the goal. Goal is this full position, but I want to use minimum energy, right? I don't want a black dog running around too much. So again, I'm going to do a quick live demo. So this shunting game, the specification pretty similar to what I have. The verification is that we want to reach the goal with the minimum energy. That is the shortest path. And we verify. Model checker, I think this using online model on-the-fly model checker generates the entire state space and searching to the state that is reachable to the goal. And is reachable. And this is the minimum number of steps. And if they give me a simulation. Okay, there's an initial state. You say, tell me how the model checker solved. So model checker basically tell you that's how the black dog is moving. Show you the trace which leading to all the Y shape is moving in the drop position. And it show you the position of the black dog, the C position, R position, and the board configuration if the white board is changed. And you can see that's the how model checker is solving this by producing the shortest trace leading to this reachability from initial state to the final goal state. Okay, got idea. So this pretty much the major idea of model checking in the concurrent systems. You may say, what current project is using PAD? There are many different applications. Um, just using concurrent module, we have a lot of project on cybersecurity. The first project is using PAD model checking smart grid system for security and privacy. The second one is building compositional approach for security systems. There are two industry labs, Intel, Cisco, also try to use lab PAD to analyzing some attacking pattern in the traffic anomaly. There's also anti-phishing project. But today I want to get into AI area. Sun Jun actually leading with Liu Yang myself leading a MOE Tier 3 10 million project on certified AI systems. In Australia, with Joe, we actually using PAD and NPAD to help in autonomous systems. So today, I'm mainly just using these two examples, autonomous systems and sports analytics, which is very close to commercialization, has been applied to helping real player to beating the world best. For autonomous system, Australia and many countries have developed many drones. Many hardware has been developed. But the question is, what is the software behind those hardwares? On the right-hand side, there's a yellow one. It's developed by Australian Defense Department. It's called Debris. It can go into the underwater for months. The problem is that the underwater current is unpredictable. If the travel routes was not well planned, dynamically controlled, then we're going to lose those devices easily because undercurrent just don't have enough time to come back fully recharge the battery. When they run out of battery, that's it, you lose it. So the project is about using PAD making goal selection, planning to interact with the AI systems developed inside those autonomous systems. Detail, there's a paper, Gravitas in Engineer Applied AI journal. The key idea is like this. You start autonomous position at H, try to visiting different position, A, B, C, D, E, F, D, and then go back to position R to recharge the battery. Initially, PAD will calculating a travel route starting position A and B and go to C and D. Give the partial geography information. It will give a ultimate travel routes, just like the shunting game, right? give the shortest trace leading to push all the positions into the middle. Similarly, you can calculate a trace to use the minimum energy. In real time, however, after you visiting position A, you may find enemy in front of you to cut you off from position A to B. On the fly, Pat will make another decision to say, okay, this could be the way to visiting all the routes. However, after this calculation, we know that it's just not enough battery. Therefore, Pat will make another dynamic decision to remove the least important position D and visiting most important position A, C, B, D, then go to recharge the battery. So that's one of the project funded by Australian Defense. Joe just had another project funded by Australian Defense. So it's good. It's hard to get funding in Australia, but I think it looks like pretty successful in getting defense funding in Australia. The next one I want to get into probabilistic reasoning is I want to use a classical example called multi-hole problems. Multi-hole problem is based on American or Canadian TV series. Idea is that the TV host have a three door in front of the stage. They ask one of the customer, come to the stage, try to win the car. So choose which door is possibly to have the car, right? If the customer choose door number one, then the TV host, he will actually try to whatever trick you or try to help you. He will open the door number three to show you the gold and ask you a question, would you like to change your mind? Would you like to switch your decision from number one to number two, right? So what's your strategy? Should always switch? Should not always switch? A lot of people actually said, it doesn't really matter because the chance of winning a car is just 1/3 of a chance. There's only one car, the rest is two gold. If you study statistics subjects, you may realize that maybe taking the strategy always change your mind. If you open door number three, you change from door number one to number two. If you open door number two, you change your decision from number one to number three, because that kind of will increase the twice of the chance of winning. Just make a system slightly more complicated, because that's easy to do, to calculate using pad. Imagine we have a device. When you choose door number one, we open the door number three, then we push a button. Behind the scene, there's some kind of noise, and 1/3 of a chance they're going to put the car behind door number one. And the TV host even tell you the behavior of this particular button, pushing this particular button, making certain noise behind the scene. And then what's your decision to make, right? So you can simply just specify what the problem is in pad. So here's a probabilistic model in pad. Here's a car, here's the gas, here's the gold. Here's the decision is initially is false. The goal is try to guess a car, and the decision final equal true. First action is the TV host place the car behind the door, behind door number 1, 2, 3, 4, place the car. And then the user will make a guess. 1/3 of chance, the user will make a guess door number one. 1/3 of chance choose door number two. 1/3 of chance will choose door number three. And TV host will show you the gold. Then that is open the door. It's not a car behind it, obviously, and also not where you have guessed. If you choose door number one, then you open the door number three. That's show you the gold. Then try to take an offer. If you take the offer, you basically say, okay, I'm going to change your mind. And you're going to take the offer, you change your original guess to the things you're not original guess door number one. It's not the gold, we'll change to door number two. Okay. Or you can say, okay, it doesn't matter, I'm just lazy, just 1/3 of chance winning. Don't bother me about it. My decision is final. And you say, well, what about the switch device? The switch device is that when they show you the gold, um, and then push a button, one third of a chance. Actually, they actually switched car behind what you original guess, door number one. And all this assertion just check which decision is better. So maybe let me do a quick demo. Uh, Here's Pat. Again, this building example. This is the one I demonstrate in my slides. And the assertion is either you take the offer or not to take the offer. System take the offer, the TV host place a car, user do the guess. I choose door number one. It show you door number three is gold. If you take the offer, means you switch your decision from door number one to number two, right? So that's the idea. Firstly, let's verify. Not to take offer. Not to take offer is not to take offer is what? Not to take offer is to place a car, guess, show you the gold, and you say I'm not going to take the offer. I'm still keep my original decision, door number one. So that's the idea. First, let's calculate the winning chance of winning the car. Everyone believes should be one third of chance, which indeed true. Minimum winning chance, one third of chance, maximum one third of chance. Now, what about always take the offer? When they open door number three, you automatically say, I'm going to switch to door number two. Is that going to be a difference? In fact, indeed, they actually increase the winning chance by 2 times. Okay, the intuition between for this explanation is that because the original guess to guess a car is only one third of a chance, therefore you get after your first original guessing the gold is 2/3 of a chance. Under this assumption, let's say you indeed choose a gold, right? That's a 2/3 of a chance. Under this assumption, if a TV host open the door to show you another gold, if your original guess is a gold, he show you another gold, the one left must be a car. Therefore, if you every time you switch, you get a 2/3 of a chance winning. Okay, so you can play around, try to understand that if you haven't seen this example. But what about this host switch, right? With a button switch around the car, one third of a chance, switch the car. That's getting more complicated. So this time, if you change your mind with this secret little button, your winning chance will only 40%. And if this time you're lazy, you don't want to change, not to switch, you actually have more than 50% chance of winning. Okay, so that's the basic example of probabilistic model checking. Probabilistic model checking are very good for calculating a safety critical system like an aircraft is 99.99% reliable if you know the component of aircraft, the wings reliability, engine reliability, sensor redundancy reliability, um, if we know those reliability of the components, we can easily calculating the overall aircraft reliability. So that's what the traditional probabilistic model checking are very good at application domain. But we want to apply this to sports. The idea that probabilistic model checking is very good at right, calculating aircraft reliability. If we know the wing reliability, engine reliability, sensors kind of redundancy, structure reliability, we can calculate aircraft reliability. Almost like the winning chance of the aircraft survive. Yeah. Now, we basically the first team to push this technology to sports. Now you can think about Roger Federer as an aircraft. And his serve is just like his engine, his forehand is like his wing, his backhand, and his drop shot, his volleys are like his sensor structures. And those probability of his individual serving consistency accuracy percentage in the past 3 years is easily to calculate based on historical data. So in sports, we can actually get much more reliable data based on historical to very accurately calculate how reliable a tennis player is. one particular example, fascinating in the last 10, 20 years in the tennis history is between Roger Federer and Rafa Nadal. Before 2017, Roger wins 17 Grand Slam, Nadal 14. Roger has 300 weeks number one. Nadal is, half of that. Roger has won six end of year top eight player who's the best. Roger won six times, Nadal zero time. However, before 2016, every time Roger meet Nadal, he's kind of losing. Even though all the key indication of Roger is better than Nadal, but he's actually losing to Nadal most of the time. Nadal beat him 70% of the time. So it must be some kind of strategy problem. And all the top coaches thinking about what is strategy to helping Roger to beat Nadal, given Roger is more superior, have much better forehand, moving more smoothly, better volley players technically. That kind of fascinating many top coach in many discussions to know how to help Roger to be Nadal. So that's one of the questions. I mean, these days you could, what about let's ask ChatGPT, right? Okay, so we did that. So what is a, but to do that, we had to notice, there's a change after 2016. There is actually a change. Roger started beating Nadal. Not many top coaches even realize that. Um, so firstly, we want to ask ChatGPT, what's the head-to-head between Federer and Nadal? It give us some kind of answer, pretty correct. And you can say, okay, give me all the matches, the score between you ask ChatGPT. His memory is also not too bad. Then you say which year is turning around. He can actually sense that since 2017, Roger started beating Nadal. However, the next question is, how Roger beat Nadal, right? You ask ChatGPT, and ChatGPT gave you some advice. First advice, Roger need to be serving powerfully accurately, which is useless. Every player need to serve powerfully accurately. That advice is useless. Second one is more technical way. Ask Roger to attack, to go to the net more often, because Roger is good volleyer. That advice works for average player, but Nadal top spin would zoom into a feet. That's why Roger, most player afraid of Nadal. They don't want to go to volley, but Nadal will, the top spin will zoom into feet, the next ball, you volley up, they kill you the next one. The third one, he asked Roger using backhand slice. When you backhand slice, the ball actually backspin kind of, and Nadal top spin will hit that ball even with much faster spin coming back to Roger. Roger already had that time. Problem with handle Nadal top spin. Therefore, the third one is also completely wrong against Nadal. Against average player, maybe okay. The last one, he asked Roger to, be mentally tough, just like I told my kids all the time. Just don't worry about the score. Just focus on, enjoy the tennis, be mentally tough. Easy to say, right? Everyone want to be mentally tough, but so useless, kind of. Okay, why ChatGPT make a mistake? Because I think Joe actually asked a question, gave a predicates. How Joe asked a predicate ChatGPT for if A implies B, not C implies B. If we know A is true, then we should conclude C is true. But ChatGPT says, I'm not sure. They even give a story why it's not sure. So it's a position reasoning is a problem. So future challenge of large language model reasoning is position reasoning. So that actually is kind of discussed by Sam Altman and Bill Gates in the March this year, I think. Actually, in that kind of in that particular discussion, and the Bill Gates, it's a position reasoning is a future challenge, but Bill Gates also worried about his job. He asked Sam Altman to say, hey, one day if ChatGPT tell me, Gates, you did a good job with the foundation, you're helping Africa, did a good job. But guess what? You go play tennis because I can do better job for you. Sam actually agreed. It's a kind of during the chat during the conversation, chat said, I worry about the same thing. This GDP 456 looks like the last thing I ever do in my life. After that, what I do, also not sure. So, what industry going to be popular after AGI? Surely, robotics, space industry will continue to grow because humans want to push the boundary, make everything more automated. But I also predict the two industry like esports, sports will continue to grow. And this is evidence because AI already beat the world champion chess. AlphaGo already beat the gold champion, but the two games are still popular among humans, right? In fact, car motorbike way faster than human, but we never see human racing with a motorbike. We still find the track and field very attractive, attract a lot of people's attention. But motorbike and a car will developing their own sports. Motorbike Grand Prix, Indy car, right? The new sports competition will come, but human will still remain popular against each other because that's what people like to do. So sports, esports, through industry, I predict will continue to go, particularly when people only working 2 days a week. What are they going to do for the rest, right? Play sports, esports. Anyway, so that's just a little side story. Um, but okay, ChatGPT couldn't help, right? How to beat erosion against Nadal, but what are we gonna do? What are we gonna do? We're gonna use just the probability model checker we built for uh the the previous puzzle, previous Monty Hall problem. We're gonna build a system between two players like Roger Federer and Nadal. Each actually, in fact, any kind of right-hand player was a left-hand player. So initially, so we have some variable to capture common state. Whose turn to serve? We don't know. Nadal initially 0, Federer 0. Who won? We don't know because that's what we want to predict. Or initially equal 9. Then who do the serve is a non-deterministic choice. You toss a coin and decide who's going to serve first. So it will be either Federer serve or Nadal serve. The next one, pretty interesting. In the last 4 years, online data shows that Roger, 23% serving T get to Nadal's forehand, Nadal's left hand. And Roger from the deuce squad is 15% making error when he's serving T will trigger Roger Federer's second serve. Roger use 30% serving wide into this area while serving Nadal's forehand. So wide will be backhand, Nadal's backhand, Nadal's left hand. Yeah. And making 11% mistake will trigger Federer second serve. Federer use about 14% serving to the body, trigger Nadal either backhand or forehand non-deterministically. This is non-deterministic choice. Here's the probabilistic choice. So this is the classic Markov decision process model. If everything is probability, it's a Markov chain model. So when you serve body 7% mistake, will trigger Roger second serve. As you can see, Roger's second serve, the probability distribution are very different from first serve. It's much more conservative. It hardly serving to Nadal's forehand. And it hardly make a mistake because if you make a mistake, it's double fault. Nadal will get an extra score if they play 7-point tiebreak. It's a piece of program. So you may wonder where the data come from. Well, there is online data, which is built by tennisabstract.com. The data looks like something like this. So this is a Roger Federer versus Andy Murray. So Roger first serve down the tee, second serve to the body, and so on. We take this data then to calculate the average probability parameter of last 2-3 years or last 12 months, whatever the interview you like. We have many different kind of models. With that, you can do a lot of different kind of analysis. And another thing, you can do precise predictions. So here's the results, right? 2000 Wimbledon 2023. Novak Djokovic just beating Alcaraz in French Open. Everyone think Djokovic gonna win Wimbledon. He already make his jacket. If you see his jacket in US Open, actually that jacket, white, green, it was made for Wimbledon. He also believed himself gonna beat Alcaraz. He just beat Alcaraz in French Open, and Djokovic haven't lost Wimbledon for what last 5 years. Alcaraz hardly have any experience in the grass. But guess what? IBM predict Alcaraz is going to win against all the different past champion betting companies. Macro thinking surely you're going to win. Macro even laugh at IBM. How IBM predict Alcaraz is going to win? Our prediction also Alcaraz to win, but we believe that IBM's prediction was even the IBM stock went up after Alcaraz won, but 55% was way too high. The actual match is much closer to what we have predicted. The actual match is that there are 5 sets, 23 games each, only 2 point difference. So 49%, our prediction is better than IBM. But prediction who to win is not exactly what we most interested. We interested is that to helping player to beat each other. In 2015, we published paper in IEEE to state that basically in that paper, the result analyzed Federer should play more backhand down the line. And that information, well, even though we published in 2015, not many coaches read it, right? So in 2016, I was taking my kids actually to December Showdown. There's a coach meeting. I meet with many coaches demonstrate that if Federer can using, you know, off-season December, practice maybe a half hour every day on his backhand, particularly on backhand down the line. If he can improve 2%, he can improve almost 5% chance to beat Nadal. Actually, this is a live demo I demonstrated to the coach in the end of 2016. So that's this one. Right? This is the initial model, Federer serve 23%, just like in my slides. That's the model between Federer and Nadal. And those parameters are automatically generated from online data tennisapp.com by we developed even extraction algorithm to calculate the average of the last 3 years, 3 months, 1 year data. What we show is that Federer making about 18% mistake on backhand on Federer backhand down the line. Return his backhand basically making about 18% mistake. Now, what do we demonstrate that if we can change that, so Federer have chance. But before that, we want to verify what's the chance of Federer winning, right? So Federer against Nadal's winning chance is that, remember the multi-hole problem give minimum chance winning, maximum chance winning? Because of non-deterministic choice create a different value. The Markov chain will give the same value, but Markov decision process give you a range. Federer winning chance against Nadal in 2016, before 2016 is 14% minimum, 47% maximum, both below 50%. That actually formally verified that Roger loses to Nadal. Now, we don't change any of the 300 other parameters, forehand serve, nothing changes. If we just improve 2% to cut 18% to 16%, and put that 2% to down the line, right? 18 plus 2 give us 20. As you can see, I didn't touch anything else. Now, if we verify, I didn't touch any 300 other parameters. The final chance for Federer beating Nadal before was 46, 47%. Now, the minimum is already over, right? 50%. And the maximum is almost 51%. So both minimum, maximum below, above 50%. Now Federer can beat Nadal. I guess it was good demonstration to many coaches. You know, Roger has many coaches. His first coach from Australia, his other coach also a lot of Aussie. Tony wrote his coaches. Some of the coach pass a message to Roger. Roger actually is such a good student. During that, we had all the data shows in 2017. Roger actually improved his backhand down the line more than 2%. End up what? End up 3%. I think my PhD student Joe calculate 3 or 4% improvement on his backhand down the line. And that was the reason Roger actually beating Nadal every single time during 2017. And since his rest career also only lost to Nadal once in French Open. I was joking that Roger make a big mistake. The reason is, our suggestion in 2000, end of 2016, whatever passed to him on, he didn't really pay any appreciation to us. So what are we going to do? We're going to help Nadal to beat him? That's too easy, right? we're going to help a lower ranked player, which never beating Roger before. So John is Millman is also Brisbane. It's also used to practice with my son Chen. The professional Australian player need a nature the junior, so they often practice with top junior players. Chen was number one junior at that time, and John actually a good friend with Chen and a good friend. So I was also having John's. This is my email, my business card. This is the day 1 day before he played Roger. Even before he played Roger, we're sending all different probability report. And in the U.S. Open, John has never beaten Roger. Actually, in John's life, his entire career, never beaten any top 10 player. And Roger has never lost to anyone outside top 50 in his life during U.S. Open. So that time, if you put $1 win for Roger to win, if Roger win, you get $1, you get 3 cents back. You put $1 for John Millman to win, you get $19 back. So we are not want to take a credit of John. John actually indeed beating Roger during the US Open. I got a thank you message, from John. So this is evidence we have. And that creating big news. Guess what's interested? Clean one day say, hey, what? Djokovic data science, they try to get your number. Did they call you? I think they try to get a story behind the techniques. And obviously, Djokovic is very interested in this. This is just one of 2020 we meet up. Chen actually had 1 hour practice with Djokovic. In this particular practice, also show one particular weakness of Djokovic. It's a similar kind of pattern because if you have a very heavy spin into Djokovic forehand deeply, he didn't take that step back, create that space, and he may have an higher error rate on his forehand side when you hit a top spin into his forehand. Let's say this rally. So Chen forehand played the junior Grand Slam that time, so they practiced together. Slice, Chen top spin, very heavy, top spin, boom. Djokovic made a mistake, right? So Roger has a similar mistake on his backhand side. This is one particular pattern. Helping professional player is easier because they level almost to perfections. So a little bit of strategy change will create a big different outcome. But helping junior player, social player is the next challenge. It's also because there are not many online data available. Tennisabstract.com only provides professional players. So what we need to do is using video analytics. So this is the system we developed using computer vision deep learning to automatically capture. This one Chen still play for Georgia Tech at that time, I think. Wow, this is yeah. And oh no, already LSU, I think. Yeah. And this is tracking the ball, tracking the player at a different position, map into the precise position of the tennis maps, right? So I also provide advice for uh, for LSU coach, they need to play more backhand, more butterfly. I think in some sense helping the college level. But we also using large language model to do the video analytics. For example, we can divide the video into multiple frames. So this particular action, for example, Nadal, Federer, those kind of rally. If this video we large ChatGPT GPT-4 video and give us information. The general information pretty good. They can recognize this Wimbledon, grass court, Nadal, Federer, score is what. But the detailed action recognition sequence, he only get about 50% correct. The rest, right? Just GDP just not good at it. So what do we need to do? We also need deep learning, computer vision, our own technology. We get to about 90% to 80 to 90% accuracy, which is much better than 50% accuracy of GDP4. Stanford has a better result a couple years ago. They're about 80%. Now we are better than Stanford. We actually have the best computer vision recognition video analysis for fast action sequences. Also project on sports injury using the IoT devices, analyze sports injury. Yeah, the general framework is that whatever the big video data or online data, we're using probabilistic reasoning with the machine learning to make decisions. Doesn't matter for sports or military or environmental prediction or security. So that's the major kind of framework ideas. So the new company we want to build is really try to combine large language model with a formal method agent like PAD. Be able to train the LLM agent to become expert writing PAD model automatically, then certify some kind of a design, some kind of software are correct using PAD model checker, self-correcting, self-verifying. And maybe the pipeline that LLM will do certain parts, and the public model checking will do some other kind of analysis, like the sports we demonstrate as example. We also have other project in fintech. We're on the way with many medical faculty, dentistry in US, have many joint projects. We want to push that direction. And also this automatic programmer, once Hai Yufan is looking at try to produce verified code from informal requirement specification through formal stepwise um, uh, requirements uh, called program refinement. Those are many kind of ongoing projects. Uh, I just want to thank all the people working on all those projects and other projects. Uh, Thank you, my collaborators, and hopefully many of you here we can further collaborate on either on company or on the research collaborations or building a companies internationally. Yeah, so that's pretty much my part of the talk. I will leave. Yeah, there is also a sports analytics conference, which sports analytics is just one division under the new company in our vision. There are many other domains we want to push. Um, so I probably it's time let me pass to Zhe.